They never imagined that a single shell could tear an entire battleship apart. December 13, 1939. The South Atlantic is calm, almost deceptively so. The British heavy cruiser HMS Exeter cuts through the grey water when a lookout spots a shape on the horizon. At first it looks unreal, like a trick of mist and distance. But as the silhouette sharpens, the truth becomes clear. A German warship is out there. And deep inside her steel belly, in the magazines of the pocket battleship Admiral Graf Spee, something waits. Something engineered with such precision and such malice that even the men who load it into the guns do not fully understand what it will do when unleashed. This is not just ammunition. It is a weapon that weighs as much as a small car, stands taller than a man, and carries enough explosive force to vaporize steel, flesh, and hope in the blink of an eye. This is the story of the most lethal naval shells ever created during World War II. And if you think naval battles were simply about ships trading fire across the sea, you are about to discover that the real horror was not just in the fighting. It was hidden inside these massive rounds, sealed in steel, waiting. The story begins years earlier, in 1936, deep inside the steelworks of Essen, Germany. Inside furnaces so hot the air itself seems to shimmer, engineers face a problem that borders on the impossible. How do you sink a ship designed never to sink? By the mid-1930s, battleships have become floating fortresses. Their armor belts are thicker than walls of concrete. Their decks are layered in hardened steel. Conventional shells no longer shatter them. They bounce, crack, or explode harmlessly outside. And across the world, Britain, America, Japan, and Germany are locked in a silent arms race, each trying to build ships that can survive anything the enemy can throw at them. But armor is only half the equation. Germany's engineers understand this. If armor cannot be defeated by brute force, it must be defeated by precision. What they set out to create is not just a shell, but a carefully engineered sequence of events, a mechanical chain reaction designed to end with a ship dying from the inside out. It begins with the casing. Each shell is forged from a single piece of hardened steel, heated and hammered over and over again, then cooled in carefully controlled patterns that align the metal's internal structure in ways that do not occur naturally. The steel must do two contradictory things at once. It must be hard enough to punch through more than 16 inches of battleship armor, yet tough enough not to shatter when it hits. Finding that balance is like trying to make glass that can be used as a hammer. The forging process alone takes weeks. Workers feel the weight of these shells in their hands and know instinctively that this is something different. When you stand next to a finished naval shell, when you see it up close, you realize this is not simply ammunition. It is industrial art twisted into a nightmare. Artillery turned into inevitability. But the casing is only the beginning. Inside the steel body is a hollow cavity, and what goes into that space determines whether a ship lives or dies. The explosives are not simple gunpowder. They are compounds with names like TNT, amatol, and shellite. Chemicals so volatile that a single mistake could erase an entire factory. And yet more than 300 pounds of high explosive are packed into each shell, compressed into a space barely larger than a trash can. Enough force to level a city block, sealed inside steel. Still, the engineers lose sleep over one question. How do you make sure all of that explosive power detonates at exactly the right moment? Too early, and the shell explodes before penetrating armor. Too late, and it passes straight through the ship, wasting its destructive potential. The answer comes in the form of one of the most diabolical devices ever created for war, the delay action fuse. This tiny mechanism sits at the tip or base of the shell. It must survive the unimaginable violence of being fired from a naval gun, experiencing forces over 40,000 times the force of gravity, enough to liquefy a human body. Then it must survive smashing into hardened steel at over 2,000 feet per second. Only after all of that, only after the shell has buried itself deep inside the enemy ship, surrounded by machinery, ammunition, and men, does the fuse activate. German Type A fuses are mechanical masterpieces. Springs, pins, chemical delays, all working in perfect synchronization. Inside each fuse is a tiny vial of acid. On impact, the vial shatters, and the acid begins eating through a thin metal barrier. Roughly 3/10 of a second later, the barrier fails. The detonator fires, and hell erupts from within. To understand what that means, imagine May 24th, 1941. You are a sailor aboard HMS Hood, the pride of the Royal Navy, the largest battlecruiser in the world. The sea is cold in the Denmark Strait. Far away, almost beyond sight, the German battleship Bismarck opens fire. From 14 miles away, shells weighing nearly a ton arc into the sky, traveling so fast they create their own sonic booms. You never hear them coming. And then one strikes. In less than 6 seconds, the shell punches through Hood's deck armor as if it were paper. It penetrates 40 feet into the ship's interior and detonates next to 200 tons of cordite propellant. The explosion is instantaneous and absolute. Hood breaks in half, her spine snapping like a matchstick. Of the 1,418 men aboard, only 3 survive. The rest are vaporized, crushed, or trapped as the wreckage plunges into the sea. All because of what was hidden inside that shell. And what makes these shells truly terrifying is that they are not merely designed to penetrate and explode. They are designed to create cascading destruction. Naval architects know that the real weakness of a warship is not its hull, but what lies inside it. Engines, fuel, ammunition, crew. When the shell detonates, it does not just produce blast pressure. It shatters its own casing into thousands of high-velocity fragments, each one a jagged piece of steel traveling faster than a rifle bullet. These fragments tear through bulkheads, pipes, wiring, and bodies. When they strike ammunition or fuel, they trigger secondary explosions. Those explosions create more fragments. Within seconds, a single hit becomes a spreading catastrophe that moves through the ship like a disease. The Japanese learned this lesson at Leyte Gulf in October 1944. American battleships fire 16-inch armor-piercing shells, some striking directly, others missing by only a few feet. Even underwater, the shells retain so much energy that they punch through hull plating below the waterline. The fuses still function. The explosions still occur deep inside the ships. Flooding and fire combine into something no damage control team can stop. The physics behind this destruction is brutal and fascinating. When a shell hits armor at high speed, both materials deform. Enormous heat is generated, briefly melting steel at the point of impact. The outcome depends on angle, velocity, and hardness. German engineers solved this problem with capped shells, using a soft armor-piercing cap to absorb the initial shock and prevent shattering, and a ballistic cap to improve flight stability. On impact, the caps deform and fall away, allowing the hardened body to drive through the armor, which fails not by cracking but by being stretched until it tears. Other nations follow similar principles. Different designs, same objective. Maximum kinetic energy. Maximum internal damage. Detonation in the worst possible place. The men who load these shells rarely understand what they are handling. In dimly lit turrets and magazines, illuminated only by red lights, they move hundreds of tons of explosives under combat conditions. They know that if an enemy shell reaches them, they will never feel it. The explosion will be too fast. At Guadalcanal in 1942, USS South Dakota absorbs dozens of shell hits. Some fail. Some penetrate. The ones that explode turn compartments into sealed killing chambers. Survivors later describe walking through twisted corridors where metal and flesh are indistinguishable. And then there is the Monroe effect. By shaping explosive charges internally, engineers learn to focus detonation energy into cutting jets of molten metal. While not fully developed during the war, the principle makes shells deadlier, turning explosions into burning, drilling forces rather than simple blasts. The Japanese pursue a different philosophy. Their Type 91 armor-piercing shells are massive, elongated monsters designed to fall at steep angles and punch through deck armor. Converted versions of these shells strike USS Arizona at Pearl Harbor. One detonates inside the forward magazine. The explosion lifts the bow out of the water before the ship disintegrates. As the war grinds on, engineers focus on fuse reliability. Base detonating fuses. Combination impact delay systems. Detonation rates soar from 30% to over 80%. 8 out of 10 hits now produce catastrophic internal explosions. Some German designs even experiment with rocket assistance to extend range. The shells are never perfected, but the ideas survive, influencing post-war artillery for decades. None of this works without targeting. Hitting a moving ship from 15 miles away requires mechanical computers, analog fire control systems packed with gears and cams. At Surigao Strait in 1944, American battleships use radar to fire in total darkness, striking Japanese ships that cannot even see their attackers. As the war grows more desperate, shells become even more horrific. Incendiary compounds are added. White phosphorus, thermite, materials that burn hotter than water can extinguish. The goal is no longer just to sink ships, but to make survival impossible. And then there is the sound. A 16-inch shell travels at nearly 3 times the speed of sound. Survivors describe it as a screaming freight train. You hear it. You wait. You pray it isn't yours. Near misses are often worse than direct hits. The pressure wave alone can rupture hulls below the waterline. Ships slowly flood, list, and die. If a shell reaches the engine rooms, the result is unthinkable. Boilers rupture. Superheated steam floods compartments at hundreds of pounds per square inch. Men are cooked alive. Doors are sealed to prevent the steam from spreading. The screams echo through the ship, then stop. This is the part of naval warfare history rarely discussed. These shells do not just sink ships. They erase people. By 1945, the ultimate evolution arrives. The American 16-inch Super Heavy shell. 2,700 pounds. 440 pounds of explosive. Kinetic energy equivalent to a freight train at highway speed. Nothing can stop it. And yet, even as these weapons reach perfection, they become obsolete. Aircraft now dominate the sea. Torpedoes and bombs strike from above. Battleships fade into irrelevance. The last battleship duel occurs in October 1944. After that, the guns fall silent. Ships are scrapped or turned into museums. Thousands of shells are dumped into the ocean, still dangerous, still intact, lying on the seabed like dormant monsters. 80 years later, some of them remain chemically stable. Waiting. The men who designed them are gone. The men who fired them are gone. The men who died by them are gone. But the shells remain, behind museum glass, on the ocean floor, silent evidence of a time when humanity poured its brilliance into perfecting destruction. Each one represents not just technology, but choice. A decision to build something whose sole purpose was to tear apart other human creations and the people inside them. And that is the legacy of the most lethal naval shells of World War II. If you want to uncover more hidden, unsettling truths from the history of warfare, make sure to subscribe. Another story is coming very soon, and once you hear it, you won't look at history the same way again.